Paramaradana, hope you're doing good. So due to, as I said in the WhatsApp chat, due to network issues, I have come home because of network issues. I'll be taking few classes in the online mode. Basically, I'll be doing a video presentation and then I'll share the link with you. So for next couple of few classes, we'll continue like this. And if you have any doubts in the classes that are going on currently, then you can WhatsApp me. I'll either contact you through call or I'll write a detailed solution of your doubt and send you through WhatsApp. So now, before moving on, let us summarize what we have done in the previous classes. We have started with this solutions chapter, which is nothing but mixture of solute plus solvent, and we have studied its common types. Basically, the common types are like uh, solid in liquid solvent, and then gas in liquid solvent, and then another common type is gas in gas, or solid in solid. We have studied this, right? Solid solutions, solid in liquid solution, gas in liquid solution. So then we went on to study composition and units. Composition is nothing but how much amount of solute you are adding into solvent to make a solution. So since you are adding some amount of solute into a solvent, and then you need to know how much your solute is composed of in the solution. For that purpose we use units. So some of the units that we have studied is mass by mass, volume by volume, and molarity, and simple unit is how many grams per liter, and then molality, normality we studied, and then another important one is mole fraction. So these are the some of the units that we have studied, and these are very important whenever you are doing problems. So units you must take care. And then properties of the solutions. So basically the properties that we have studied till now is, one is intensive property, another one is extensive property. So hope you remember what is this intensive and extensive property. Intensive property is the one which do not depend upon the uh, mass of the solution, and extensive property is other way around, that do depend upon the mass of the solution. So yeah, the properties which do not depend upon the mass of the solution are intensive properties, and that depend upon the mass of the solution are extensive properties. To give you example, the intensive properties are like temperature and density and concentration, etc. Whereas extensive properties, to give you example, like volume, so volume, number of moles, all those properties are extensive properties. And then next thing we have studied is non-volatile substances. So in this case we have studied one, like here we have studied non-electrolytes, and then we have studied electrolytes. Basically it involves the dissociation, whichever the compound that do not dissociate but it's still soluble in solvent, those we call it as non-electrolytes. For example, like sugar which do not give any ions upon dissolution but still it dissolve in the solvent. And there are electrolytes. In the electrolytes also we have one is called strong electrolyte, another one is called weak electrolyte. So we have studied this in detail. Strong electrolyte, to give you example, NaCl. So whichever completely dissolves or 100% dissolves in water and give you ions, After dissolution, those we call it as strong electrolytes, whereas weak electrolytes are the ones even when they are dissolving in a solvent but they do not completely dissolve, they'll give you partial ions. For example, this acetic acid CH3COOH, it do not it won't completely convert into ions, that is CH3COO plus H plus ion. So suppose if you have 100% of this, only about 30 to 40% of ions you will get, rest of the amount of acetic acid will remain as CH3COOH instead of dissociating into ions. Another concept is dissociation and association. We have studied like the dissociation, just like in this case strong electrolyte and weak electrolyte, where our electrolyte is getting dissociated before getting dissolution, whereas association is nothing but suppose if you have a solvent like solute like CH3COOH, which is capable of forming hydrogen bonds, so it can convert into dimer and tetramer or trimer. So because of this, the number of solute molecules that we have started with will be more compared to the number of solute molecules that are present in the solution, whereas in case of dissociation, the number of solute molecules, for example, I'll take NaCl as the example. When it dissociate, it will completely dissociate into Na plus and Cl minus. So as a result, we might have started with few moles of NaCl before getting dissolution, but after they get dissolution, we'll be having double the number of ions present in the solution. That is because each molecule is getting dissociated into positive and negative ion. That is why we'll be having more number of ions in the solution, whereas in case of association, since one compound is getting associated with the another compound, you will be having less number of molecules in the solution. So another concept that we have studied is Henry's law. Henry's law we have discussed in detail. This concept basically comes when we have the solution of gas in liquid, just like soda, where we are dissolving carbon dioxide into water, or just like acetic acid or any other acid, where we are dissolving HCl gas into water to make it acidic. Here the Henry's law says that amount of pressure that you are applying in the gas will be directly proportional to the amount of mass that is present in the solution. So the more pressure you apply, the more gas it will dissolve. This is the Henry's law. And then we have studied the mechanism of dissolution, in which we have studied two things. One is solvation sphere. Because of solvation sphere, the ions are getting dissolved. For example, if you have NaCl, where it can dissociate it into Na plus and Cl minus. In this Cl minus, because it is having negatively charged ion, and we are suppose our solvent is say water, where it can dissociate into H plus and OH minus. These H plus ions will form a solvation sphere around the Cl minus ions. So as a resultant, because water is having high dielectric constant, it will these hydrogen ions will go around chloride ion, so that this chloride ion is very far away from the Na plus and they do not get attract each other. In the similar to H plus ion, here it is OH minus ion. It will form a solvation sphere around NaCl, sodium ion, so that the sodium is unavailable for the chlorine, so that they do not come together and form a NaCl molecule again. This is the mechanism of dissolution. One is solvation sphere, another one is hydrogen bonds. This is similar to this case, but here let us take the example of CH3COO minus. Here, since you have negative charge and it is partially dissociated, and you have a partial positive ion on the hydrogen atom, These hydrogen atoms, which are having partially positive charge, will come closer to the partially negative charged CH3COO minus ion, and thereby it stabilizes this ion. In the similar manner, the H plus, which is counterpart of this CH3COO minus, is stabilized by oxygen atom, which is having partially negative charge. So these are the two mechanisms that you must know, that are involved in the dissolution. And then we have studied vapor pressure vapor pressure of the solution and addition of the non-volatile solute. So vapor pressure of the solution, for that we have studied this concept, equilibrium concept, where I told you that uh, equilibrium there is a equilibrium is achieved. Suppose if you have any liquid in a closed vessel, this is the closed vessel, and you have certain liquid here. There occurs some point, let's say this is at constant temperature is constant. At some point this liquid will try to evaporate into vapor phase, but since this vessel is closed completely, this vapor do not escape from the vessel, but what it will do is it will come back to liquid state. Thereby we'll achieve one stage where vapor phase is in equilibrium with the liquid phase. Whatever the pressure that this vapor is undergoing, so that it can come back to the liquid state, this pressure we call it as vapor pressure, which gives birth to Raoult's law. See the difference between vapor pressure and normal pressure that we have studied in the Henry's law. Henry's law, we are applying pressure outside, externally we are applying. Suppose if you have a CO2 gas and you want to push it into the water to make soda, what we do is we externally apply some pressure on this CO2 gas and push this CO2 gas inside water and lock it, so that the whatever CO2 gas that is present in the water do not escape. Whereas in this case it is already in a closed vessel. This liquid at a certain temperature, it is trying to escape, just like when we boil rice in a cooker, where our cooker is completely closed and water does not escape, but it will stay on top of the vessel. In the similar manner, here this vapor will try to condense back into the liquid form. Thereby it itself exerts pressure on it, and this pressure we call it as vapor pressure. Hope you understood the difference between this vapor pressure and the pressure that is being involved in the Henry's law. And as a resultant, we have Raoult's law, which completely talks about vapor pressure. So here we discussed another concept, that is addition of non-volatile solute. So what happens is, every solvent will be having certain vapor pressure that we call it as pure vapor pressure. We represent it by P naught. Whenever you add some non-volatile solute, by name itself it is saying that it is non-volatile. That means it it doesn't want to escape from the solvent. So since it doesn't escape from the solvent, what happens is this will form a layer at the top of the solvent, so that the solvent molecules do not escape from the water. So as a resultant, the overall vapor pressure will be reduced. So because of addition of non-volatile solvent, vapor pressure of the solvent will reduce. This we have discussed. If you have any doubt, please go back to the previous classes and see. And we have studied Raoult's law for both ideal case and non-ideal case. What does this Raoult's law says? Raoult's law says that vapor pressure of a solution is directly proportional to, is equal to vapor pressure of the liquid in its pure state into its mole fraction. Suppose if you want to find out the vapor pressure of you have a homogeneous mixture where you have two components A plus B, and the question that they are asking you is to find out the vapor pressure of just A. So that time, what does Raoult's law says? Raoult's law says that vapor pressure of A in a solution of A plus B is directly proportional to mole fraction of A. That means if you have a more fraction of A, you will be having more vapor pressure. If you have a less mole fraction of A, you will be having less vapor pressure. And if you neglect, if you remove this proportionality symbol, you will get the expression of Raoult's law something like this: Pa equal to Pa naught. This Pa naught is nothing but vapor pressure of A, component A, in its pure state. Pure state means it is not mixed with the another component like B. So when it is in pure state, what is its vapor pressure? And that is what we call it as pure vapor pressure. And this is multiplied by mole fraction of A. Similarly, for component B, Pb equal to Pb naught into Xb. And Raoult's law says that uh, the vapor pressure, total vapor pressure of solution is equal to vapor pressure of component A plus vapor pressure of component B. This is the expression that you must remember. This is what Raoult's law, and this is Henry's law. Hope you understood the difference between Henry's law and Raoult's law. Let me explain once again. In case of Henry's law, the pressure is applied from external source, whereas in case of Raoult's law, the vapor is the whatever vapor which is in equilibrium with the liquid phase is itself applying pressure on it, so that it will condense back to liquid state. And this Raoult's law, we have seen it for different cases, ideal and non-ideal solution, and we have seen the differences also. The major difference between ideal and non-ideal solution is ideal solution will follow Raoult's law, whereas non-ideal solution will not follow Raoult's law. As a resultant, this px diagram, here P represents the vapor pressure, whereas the X represents the mole fraction. For ideal case, these px diagrams are straight lines, just like this. Hope you remember this concept. Hope you remember this concept. And for non-ideal case, there is either positive deviation or there is a negative deviation that is being observed. And we studied why there is a positive deviation, why there is a negative deviation, and what are the forces of attraction that exist, so that in case of ideal non-ideal case there is positive and negative deviation. These all things we have studied. If you have any doubts in these concepts that I have summarized just now, please please tell me, so that we can discuss in detail, or I can give you in a written format so that it will be clear for you. Next thing, till now we are studying about the solutions. So solution is nothing but a mixture of two components, let's say A and B, and it can be a miscible liquid or immiscible liquid. If it is immiscible liquid, just like oil in water, oil plus water, where both of them are immiscible, then you can clearly see that oil is forming a different layer and water is forming a different layer. As a resultant, just by using some separatory funnel, you can easily filter this out. Means you can easily separate it out. Whereas when you have a mixture of A and B, this time they are forming miscible liquids, just like alcohol and water. So that time how can you separate? What technique do you use so that to separate this? Obviously, one thing that comes to your mind is distillation. Fractional distillation. What is the principle that is involved in the fractional distillation? You know very well that is difference in the boiling point. That means if you have a liquid, one is boiling at say 30 degrees, and if you have another liquid, one is boiling at 70 degrees, you control the temperature to 30 to 40 degrees, and this 30 degrees component, say A, this will evaporate. When it evaporate, you try to condense it with a condenser where you are maintaining a cool temperature. So since whatever vapor at 30 degrees is evaporated, will condense it back to another vessel, thereby you can separate easily. But what if you have a two components A and B, those components at certain composition, I mean, what do I mean by certain composition? Some percentage of A and some percentage of B at a fixed composition, they they are not separable, means you cannot separate them even by using a fractional distillation technique. So even if you, because it acts like as a solvent, one single solvent, it will act like. So because of this reason, even if you heat to those temperatures, and this entire liquid will convert into wafer phase instead of only one component being converted into wafer phase. And these type of liquids, these type of mixture, we call it as azeotropes. So let us see the definition. See, a solution of completely miscible liquid at definite composition. This word is very important because only at one particular composition they will act like azeotropes, means they will act like a single solvent instead of two miscible liquids. I'll give you example, that time it will become even more clearer. What happens is, miscible liquid at definite composition boils at a constant temperature. See, the temperature is constant, that means you have to use thermostat at one single temperature. They will act like a pure liquid, just like only one component is present in the mixture, just like that it will act. So distilled over without change in the composition. Even if you heat it, there will not be any change in their composition, and these mixtures we call it as azeotropic mixture or constant boiling mixture. So these are very difficult to separate. For example, this ethyl alcohol and water. I was telling you it should be definite composition. Here the composition is ethyl alcohol is 97.5% and water is rest 2.5%, and constant temperature, the temperature is 315.15. So what happens is, this solution, here it is given that the solution boils at a constant temperature. This act as a one single solution, one single solvent or one single liquid, and this entire liquid will combinedly boils at this particular temperature, that is 315.15. So even after some period of time, suppose say here time is 0 minutes, and you boiled this solution at the 315.15 Kelvin for say 15 minutes, and since you are boiling at the boiling point, you know, right, vapor is in equilibrium with the liquid phase. Suppose if it is in a closed vessel, if it is not in a closed vessel, the vapor will evaporate at the boiling point. Just like if you heat water at 100 degrees, the water vapor will evaporate if you, unless or until you close the vessel in which you are boiling. So even in this vapor, say after boiling, some vapor has released and there is some liquid. In this liquid also, the composition, if you measure the composition of both the components, ethyl alcohol will contribute 97.5% and water will contribute rest of the amount 2.5%. Even in the vapor, even in the vapor, if you measure the composition, it will be same 97.5% plus 2.5% of water. These type of liquids, so we call it as azeotropes, and these cannot be separated by a fractional distillation. Hope you understood the definition of azeotrope. And these are usually non-ideal solution. This point you must remember, there is a chance of asking this point in the competitive examination. What are azeotropes, ideal solution, non-ideal solution, or both of the above, or only one of the above, like that they'll ask. So the correct option would be non-ideal solutions. So here we have studied, right, non-ideal solutions. We already studied that these will deviate from Rolle's law, and we already know that there are two types of ideal solution. One is positive deviation, another one is negative deviation. Even under the positive deviation, there are two types of mixtures. One is, say, this one is type 1 and another one is type 2. The major difference between these two is, see this deviation curve. Here in the textbook they have given little wrong. So what is this type 1 is, type 1, it will not reach maximum, means the deviation will be less than the boiling point of pure liquid. What I am trying to convey here is, here the pure liquid of B is this much, right? This is the pure liquid vapor pressure of component B. So even in the type 1 positive deviation, this deviation will not reach above this pure liquid state. It will be always below. Whatever the deviation that is occurring, it will always be below. Whereas in this case, in the type 2 case, there occurs certain point, this point, where the vapor pressure of the mixture will be maximum. Maximum means it will be greater than both partial pressure of B or A, individual component. See here, the partial vapor pressure of pure vapor pressure of component B is around this value. You can see it has clearly crossed this range and it has achieved a maximum here. This is the type 2. In the positive deviation, there are two types of mixtures. One is type 1, another one is type 2. In case of type 2, there will be a maximum deviation that is being achieved. Maximum means it will be vapor pressure of that particular composition will be greater than component B or component A. And another one we have already studied is negative deviation. In this negative deviation, there is a minimum that is being observed. This minimum point. So here, these type 2 and the negative deviation liquids, these two will be at certain composition, they will act as azeotropes. This is also important question where they can ask you, like, they will give you these three. One is positive deviation type 1, positive deviation type 2 and negative deviation, and they'll ask you to find out which one of the following do not show azeotrope, do not form azeotropic mixture. Then the correct answer would be type 1. So now let us study more into it. And here we'll be studying minimum and maximum boiling point. And this is the type 2. Till just now we have studied type 2 of positive deviation, where there is a maximum that is being observed. I hope you remember this ideal law equation, that is PV equal to nRT. No, this is not relevant here. Here the main point is the solution is having higher vapor pressure, and we know that whichever solution is having higher vapor pressure, it will boil at lower temperature. This is the thumb rule. So since at this particular composition, say this particular composition, this solution is showing maximum vapor pressure at this point, at this composition. So ideally at this particular composition, it should be showing minimum boiling point, just like this. See, this is the plot between temperature and mole fraction. This is the plot between vapor pressure and mole fraction. Since the deviation here is at this particular composition is maximum, here at this particular composition the boiling temperature will be minimum. Another thing that you must notice here is even the vapor and solution are same here at this point. These we call it as minimum boiling azeotropes. Minimum boiling azeotropes. So which type of liquids will show minimum boiling azeotropes? The liquids that will show minimum boiling azeotropes is type 2 positive deviation. Positive deviated mixtures from the ideal case will show minimum boiling azeotropes. The examples are here, like water and alcohol, acetone and CS2, and chloroform and alcohol, and the composition is given here. See, mass percentage of B, this is the mass percentage of B, 95.5. So 95.5 of B means how much A will be? A will be 100 minus this amount, then it will be 4.43, and here mass percent of B is 71.69. Here mass percent of B is 57%, and this will be 43. That means 43% of acetone plus 57% of CS2 will form an azeotrope, and it will show minimum. What kind of azeotrope it is? It is a minimum boiling azeotrope. That is what we need to understand here. See here, pure A is having 329.25 Kelvin boiling point, and pure B is having 319.25 as the boiling point. You can see here the azeotropic mixture is having boiling point of 312, which is minimum compared to these two. And you can see these figures in both cases. Here it is 351.3 and here it is 373. The azeotrope boiling point is 351.15. And similarly you can see this azeotropic boiling point is very less. It is less compared to either pure A or pure B. Hope you understood. Another concept is maximum boiling azeotrope. Just opposite to this. Here we are having maximum deviation, maximum positive deviation at one particular composition. That is why it boils at lower temperature. Whereas in case of maximum boiling temperature azeotrope, there will be a minimum deviation or maximum negative deviation at one particular composition, where it will show maximum boiling point. See here. These graphs are very important. Hope you have to understand these graphs. These are simple graphs but convey a lot of messages. See, at this particular composition, this composition, the mixture will act as a azeotrope. And what kind of azeotrope it is? It is maximum boiling azeotrope. And a few examples are here, are the few examples. See here, component is H2O, component A is H2O in all cases, and component B is HCl, HNO3, HI, HCl4, and percentage of mass is here they have given. And you can see boiling point of pure water is, this is 100 degrees centigrade, which is 373 Kelvin, and pure B is 188 Kelvin. And you can see azeotrope mixture at that particular composition, it is 383 Kelvin, which is maximum compared to pure A and pure B. These are the two types of azeotropes. One is minimum boiling azeotrope, another one is maximum boiling azeotrope. Hope you understood this concept. We'll solve few examples of till now whatever we have covered. We'll solve this example because after many days I am taking these classes of solution. So we'll solve few examples. The question is the vapor pressure of ethanol and methanol are 44.5 mm and 88.7 mm Hg respectively. An ideal solution. Here remember this term ideal solution. Whenever you heard the term ideal solution, the immediate thing that should come to your mind is it will follow Raoult's law. What is Raoult's law? Raoult's law is total pressure is equal to pressure of component A plus the pressure of component B. And even if you further explore this equation, it will become uh, partial pressure of pure component A into XA plus partial pressure of pure component B into XB. And they are telling that an ideal solution is formed at the same temperature by mixing, how much they are mixing? 60 gram of ethanol, C2H5OH, plus 40 gram of methanol. Methanol is CH3OH. When they are mixing this much amount, it is forming ideal solution. That is clear. So now they are asking you to calculate the total vapor pressure. This is the this P you need to calculate total vapor pressure of this solution and mole fraction of methanol. Mole fraction of methanol in the vapor. See, now first calculate this total vapor pressure. See, observe this expression properly. To calculate the total vapor pressure, what component you need? You need this PA0, which is a pure vapor pressure of component A. Say it is methanol. And they have given it as the vapor pressure of ethanol and methanol separately. Ethanol it is ethanol. This is ethanol. It is 44.5 mm and 88.7 mm. These we know. We don't need to worry about this. These they have given and we know. Other component what we need mole fraction. See, since it is a binary mixture, the mole fraction of both the component A plus component E mole fraction will be equal to 1. Correct? So here let us calculate the mole fraction. Mole fraction of, what is the formula for mole fraction of A? We need number of moles of A divided by number of moles of A plus B, and XB is equal to number of moles of B divided by number of moles of A and number of moles of B. So in some way or the other we need number of moles of both. So let us calculate number of moles of A. So what is the formula? Weight by molecular weight. So weight they have given it as 60 grams. A is this ethanol. What is the molecular weight? Molecular weight is 46. If you calculate this number of moles, it will come 1.304. Similarly, calculate the number of moles for B. It will come 40 divided by 40. What is the molecular weight of methanol, it is not 46, it is 32. So it will come 1.25. So we have calculated the number of moles, and now calculate the mole fraction. 1.304 divided by 1.25 plus 1.304, which comes out as 0.49, no, 0.51. And since you know component A mole fraction is 0.51, from this expression you can calculate the mole fraction of xb. What is it? It is nothing but 1 minus 0.51, which is nothing but 0.49. In this way you can save time. See, you don't need to calculate this number of moles of B at all. You just calculate the number of moles of A. No, you need to calculate because here you need number of moles of B. So once you calculate the mole fraction of A, subtract it from 1, you will get the mole fraction of B. And they have told that solution is ideal, just substitute in this equation. P equal to PA naught into XA plus PB naught into XB. So after substitution, you will get the solution. The total vapor pressure will be around 66.15 mmHg. Now what they are asking the mole fraction of methanol in the vapor. See, they are asking mole fraction in the vapor phase, right? What you need to do is, so that time it will be mole fraction is equal to in the vapor, right? So since they have used the term vapor, here what we need to do is we need to take the partial vapor pressure of methanol divided by total vapor pressure. Total vapor pressure we have calculated, that is 66.15. And partial vapor pressure of methanol also we know. How much is it? It is nothing but PA naught into XA. So PA naught we know, XA we know. If you calculate it, it will come around 22.69. No, methanol, it is not 26. Methanol is component B, so it is PB naught into XB, which is nothing but 43.46. So substitute here 43.46 divided by 22.69 plus 43.46. If you calculate the mole fraction, here it will come. See, the terms are very, very important. Here the main important term is, one is ideal solution, another one is total vapor pressure, and another one is mole fraction of methanol in the vapor. If they have asked only mole fraction of methanol, then this would be correct, this XB. But they have asked mole fraction of methanol in the vapor, so that's why we need to calculate in this manner. We need to take the partial vapor pressure of methanol divided by total vapor pressure of the solution. So hope you understood this problem. Let us solve the another problem. See, cyclohexane and ethanol at a particular temperature have the vapor pressure of 680 and it is 163, I think, yeah, it is 163. See, these are pure components. They have given it separately. Cyclohexane is having 280 and ethanol is having 163. If these two liquids having the mole fraction value equal to 0.32 for cyclohexane. See, this is very interesting part. See, if these two liquids having a mole fraction value equal to 0.32, that means 0.32 is the mole fraction of component A, which is cyclohexane. So obviously another component mole fraction, how much it will be? It will be nothing but 1 minus 0.32, correct? So it will be 0.68. They are mixed and the mixture has the total vapor pressure of 376 mm. Total vapor pressure is what? P. This is 376 mm. And they told that it is an ideal solution. Just same formula apply here. P equal to PA naught into XA plus PB naught into XB. See, in the first question, they have given this and they asked you to find out total vapor pressure. But in this case, they have given partial total vapor pressure, and they are asking you to check whether they can form an ideal solution or not. Here I didn't see the question mark. See, if these two liquids having a mole fraction value of equal to 0.32 for cyclohexane are the mixed and the mixture has the total vapor pressure 376, will the mixture be ideal solution or not? So what would be the case? If it is ideal solution, then it should satisfy this particular formula. That means total vapor pressure they have given is 376 mmHg should be equal to, what is the partial vapor pressure of component A? It is 280 into 0.32 plus 0.68 into this is it is 163. So if you calculate this, it will come around 203.84 mm. But on the right hand side we are having 376. So both are not equal, right? And that is why this mixture will not form an ideal solution, but it will form non-ideal solution. Hope you understood. We'll solve another question in the similar grounds. Same formulas, nothing to worry. Same formulas. One is total vapor pressure formula, and then mole fraction formula, number of moles formula. Here two liquids X and Y on mixing form ideal solution. So directly write down P equal to P naught X into XX plus P naught Y into XY. They told that it is forming ideal solution. At 30 degrees, the vapor pressure of the solution containing 3 mole of X and 1 mole of Y. Write down 3 mole of X plus 1 mole of Y is 550 Hg. But when 4 mole of X and 1 mole of Y are mixed, the vapor pressure of the solution thus formed is 560. 4 mole of X plus 1 mole of Y. So here in this case the vapor pressure, that is total vapor pressure P, is 560, whereas in this case 550, in this case it is 560 mm. What they are asking, when would be the vapor pressure of pure X and pure Y? What would be the vapor pressure of pure X and pure Y at the temperature? So you need to find out at 30 degrees temperature what would be the Px naught and Py naught. Let us do this. See, let us take this case where mole fraction of Xx is, number of moles of X is how many? 3, divided by total moles is 4. 3 plus 1 4. Similarly, mole fraction of Y equal to 1 by 4. So substitute, and here in this case also we'll write down Xx is 4 divided by total number of moles is 5. Xy is 1 divided by 5. These are the two different cases. Here in this case 550 equal to Px naught into 3 by 4 plus Py naught into 1 by 4. Here 560 is equal to Px naught into 4 by 5 plus Py naught into 1 by 5. This is the case 1. This is case 2. So do the cross multiplication. Here it is 550 into 4 equal to 3 px naught plus py naught, and here it is 560 into 5 equal to 4 px naught plus py naught. Equate these two equations and you will get px naught equal to 600 mm and py naught equal to 400 mm. These are the pure vapor pressure of component X and component Y at 30 degrees temperature. So hope you understood, and there is another example problem. You please try this example problem, it is easy only. The question is urea forms an ideal solution. Ideal solution means you need to write down this formula. In water, determine the vapor pressure of an aqueous solution containing 10% mass of urea at 400 degrees. So I'll give you a hint. 10% mass of urea means 10 grams of urea present in 90 grams of water. So these are the two components. Apply this formula and find out the vapor pressure of an aqueous solution. And they have given vapor pressure of water at 40 degrees is 55.93. So hope you understood the class. So I'll upload this in Google Drive and send you the link. Please watch the video, and if you have any doubts in this lecture, any doubts or any clarifications or any suggestions that you need to give me or any feedback on this particular lecture, you can WhatsApp me. I'll follow that. Hope you understood the class. I'll stop here.